Welcome back to Honors Calculus. In this video, we're talking about concavity. So the idea of a function increasing or decreasing is interesting. But another thing we can think about is how that increase or decrease is happening. Let me get my head out of the way and I'll draw a couple of pictures. Right. When a function is increasing, let's try using this pen instead. When a function is increasing, it can be increasing linearly. It can be increasing in a way where the rate of increase is itself increasing, or it can be increasing in a way where the rate of increase is actually slowing down and it looks like it's going to eventually taper off. Likewise, when a function is decreasing, it can either be decreasing in a linear fashion, it can be decreasing in a way where the rate of decrease looks like it is slowing down and is going to taper off, or it can be decreasing in a way where it looks like the rate of decrease is getting smaller, right? Larger in magnitude, but decrease is a negative number, so I guess technically that's a smaller value. All of these are possibilities. And so we want to look at another measure here. Right. Again, thinking about increase as a positive number, decrease as a negative number, if the rate of increase is getting steeper, the increase is increasing. If the rate of decrease is tapering off, then the rate of decrease is increasing, becoming less negative and going towards positive. And likewise here, in both of those cases, the rate of increase or decrease is decreasing. Rate of decrease is going downward, making it more negative. Rate of increase is tapering off. Right? So we are looking at right, the rate of increase or decrease is y prime. That's the derivative. And if we're asking when the derivative is constant, increasing, or decreasing, we can use the same tools we've used before. To figure out when something is constant, increasing, or decreasing, we take its derivative. The derivative of y prime being 0 means you have constant rate of increase or decrease. The derivative of y prime being positive means you have an increasing rate of increase or decrease, and the rate of decrease being negative means you have a decreased rate of increasing. But that's getting to be just entirely too much of a mouthful. So instead, we're going to name these things as concave up or concave down. The vocabulary shows up in a lot of the physical sciences of concave and convex. I tend to think of that in terms of lenses. Right? A concave lens is a lens that's ground to look like that. A convex lens is a lens that's ground to look like that, right? Bulging out or pinched inward. You can also think about that just in geometry terms. But thinking about that, thinking about concave. In which direction do you look at the thing and see the picture looking more like the concave lens? Well, in these first two cases, if you're at the top above it, it looks like it is concave. And if you're below it, it would look like it's convex. So that's why we call that concave up. And over here, you have to be below the curve for it to look like it is concave. If you're above the curve, it looks convex. Same thing here. If you're below the curve, it looks concave. If you're above the curve, it looks convex. That's why we call that concave down. And having a constant increase or decrease for a long stretch is called linear, but very often you'll see that happen at an instant. We're going to call that a point of inflection. And points of inflection are going to show up when we have a graph that is concave up and then transitions to being concave down, or a graph that is concave down and transitions to being concave up. So those two transition points are what we call points of inflection. All right, so there's the idea. To look and see how that actually works, let's grab some particular numbers and start playing around. How about the function y equals x to the fourth minus x cubed? Well, if we're talking about concavity, we're going to need not just the derivative, but the second derivative. So we'll take the derivative once. Y prime is going to be equal to 4x cubed minus 3x squared. And then we'll take the derivative again. Y double prime is going to be equal to 12x squared minus 6x. And we need to determine when this thing is positive, negative, or zero. So we set it equal to 0 and see what's going to happen. Well, I can factor out a 6x, and when I do that, it leaves behind 2x minus 1. Which means that we're going to have 2 points of inflection here. One when x is equal to 0, and one when x is equal to 1/2. Which is great, but it would also be nice to know whether this thing is going to be concave up or concave down. Oftentimes you can figure that out by looking at the graph, but not always. So let's look instead at a number line. So we've got x equals 0, we've got x equals 1/2, both written here, and I'm going to pick some other values. Right? Just like the first derivative test, the only way that you can go from positive to negative or from negative to positive is to go through 0. So if I pick any number over here, like say -1, and any number in between here, like say 1/4, and any number over here, like +1, whatever y double prime is, positive or negative at that point, it will be the same positive or negative at every point in that range. All right, let me scroll up a little bit so I can actually see y double prime on the screen. All right, 12 times -1 squared is 12, minus 6 times -1 is +6, so that's 18, but again, the only thing that matters is that it's positive. If I try plugging in 1/4, it gets to be a little bit messy. So we end up with 12 over 16 minus 6 over 4. All right, well, 12 over 16 will reduce. That's actually 3/4 minus 6/4, which is -3/4. But again, the only thing that matters is that it's negative. Then we plug in +1, we get 12 minus 6, which is 6. But again, the only thing that matters is that it's positive. And so we can say that on the interval from -1/2 to 0, and on the interval, I'm sorry, from -infinity to 0, and from 1/2 to positive infinity, that's where the second derivative is positive. That's where this thing is concave up. And then In the space between, from 0 to 1/2, we are concave down. In the next couple of videos, we're going to look at how to use this as a problem-solving tool. We're going to look at how to use this to do a little bit more graphing. But for right now, just knowing that we can find this is going to be good enough. So let's look at one more for you to try today. And I'm again going to go with a polynomial. Let's go with things that just drill the basic idea. How about y equals x to the fourth minus 5x squared? All right, see what you can do with this one, and I'll see you in the next video.